Hi there, Michael here, and today I'm going to talk about we can relate it to static code analysis. We're going to discuss, we're going to discuss software quality metrics, and that is how to measure things, how to put a value on your code. And we're going to do this by using a lot of static code analysis tools. Follow me here. I have some kind of agenda, and it's all about finding a way to work with good and clean codes. How to do it. It is about code quality, good code. And we want to check out here, can we actually visualize code quality? Can we sort of show an image of this is good code? Can we do that? We're going to talk about software quality metrics. So we're going to go into the deep about them, and we're going to talk general about what type of validation tools that we can work with. So sort of to measure and improve our quality metrics. And these validation tools, then they are sort of depending on what programming language we are working in. You can use different validation tools. So this is sort of a generic lecture on the topic of software quality metrics, and it's not specific to any programming language like that. Though, can we actually visualize code quality? Can it be done? Can it be measured? Can we get a picture of it? And if we can, wouldn't that be great? Because that might help us on our journey to produce good and clean code. One way to do this is what I would say is badges. So here we have a project. It's it's available on GitHub, this specific project. And maybe you have seen on those type of projects, they have these badges. And badges are sort of telling us something. The badges we have in front of us here are telling us from the top there. Top left would be sort of, this is a stable version. So this is a package and it's being handling version, and it's being released somewhere, and it has a stable version. The chat badges there just saying that, yeah, you can chat, ask questions about this software somewhere in this Gitter chat. On the second line there, we have two builds passing. So they are saying to us that whatever process this software involves, when it was sort of committed and pushed onto this GitHub, then it was checked out by a build tool, and that build run all sort of scripts available to carry out perhaps unit test, linters, code style and so, and they executed them, and that build passed without any failure. So the two builds there are two different systems that are doing the builds. So it's saying green passed. Then we have here Scrutinizer. We're going to see a bit about Scrutinizer. We're going to use Scrutinizer as an example today. So there we see it's a website for measuring code quality, and there we say that the build passed. The code was rated 6.4, and it has a code coverage of the unit test for 97%. Then on the bottom line there, we have two other code quality measurement website projects. There are also services I can use, and they are so just saying different different sort of grades of my code. So trying to say how good is the code, how hard is it to maintain, what kind of code quality it has. So here we have badges as a way of expressing good or bad code. Do you think that this is a way to go, really? So just a note on these builds. So just saying that the build passed, is that the quality measure? And what does it really indicate? Well, it depends on what we make in this build. What actually happens is that some external tool checks out our software, and then we decide what it could do with it. We could sort of provide the instructions to do make install, make test, make lint. So we can automate what it should do. And if some steps along this chain of events is sort of failing, then we will get a red badge here saying that something failed, failed. So then we know we have a problem with it. So when we relate this, green or red, so what would we choose? Yeah, I would choose the green one. The red one would somehow indicate that my fine building process has a flaw in it, and it should really be fixed somehow. So red, green. Is this somehow an indicator of quality of my project? Can it be? When we talk about quality and when we sort of talk about indicators, as I do here, how well do we really want them to express the code quality of it all? If we were, this is an example, just if we were in a court of law and we had a sort of a very bad criminal case, so the judge may sort of rule that there must be beyond a reasonable doubt that this is good code. So we need to put a lot of evidence in there. But when we are in sort of court of law, there are other levels of affirmativeness on how do I really trust you. So we have clear and convincing evidence. That is just enough to convince a jury. So I must convince the jury that I have good quality code. Or the last one here, having a preponderance of the evidence. That is the least rigorous standard. So it only says that one party should show that this is actually good code. And that is enough. So we have different levels, and I think we should also apply these different levels when we looking at these badges or processes of a sort of software project. We don't need this reasonable doubt badge if this is high quality. I think we can, we don't even need clear and convincing evidence. No, I don't think so. It is just a preponderance of the evidence. So if you as a program supplier shows these types of indicators that you are working with good quality code, yeah, that is enough for now at least. So have this in your mind when we continue to discuss about this. Another badge would be a code rating badge. So this is saying that the code can be rated between 0 and 10. And here we have a yellow one saying 6.4. So it's not good, it's average. Maybe it's okay. I can't really relate, but it's not 10. So I know that this code has some issues in it. When I put it up like this, I find it easier to relate. So my project here could have code quality like green. It's a 10. Good quality. You can't do it any better, at least according to this metrics. 6.2 in the middle, but what happens if I got a 4.3 down here? Well, that's on the red part. Is that a real issue? Oh, I don't want red in my sort of code quality. It doesn't look good. From a strict code quality perspective, that is. So yeah, I think I can relate to this code quality metrics now when I see different types of projects have different code. Okay, I want to be green. So let's see a bit more of this code rating details. So 10 is good, 1 is not good at all. And these colors we see here, they help to visualize how large part of the code is bad or good. So the green parts here, they are good. Yellow in the middle, and then we have, so this particular software here, it's more or less a quarter of it is bad. And so there we can see, we can put these colors into relations. So they tell us a bit more than when just the final value. So here we see 10. Every part of that code is pure green. If we take this one, 4, it's saying that half of the code, half of the methods, half of the classes, half of the code are rated bad. They have the worst grade here. On the other hand, 1/3 of that software has really good code parts in it. So it's only half of the code that seems to be bad, and that half code one could sort of, okay, I can focus on that and make this better. Compare that to the middle one there. So it has the green part is almost as large as the 4-dot project. But it's the red part that is much smaller, so it's less than a fourth of the sort of part of that code that is bad rated. So looking a bit behind these figures, we can get a better understanding on what are the issues in this code. This example that I'm going through now are code projects that are available from, so this is Scrutinizer, so it's a quality, it's a service for measuring quality in software programs, and you can use it on many different programming languages. So what they do behind the scene is they rating the classes. So here we see rating on the classes, and we see grades A to F. A being the best, F being the worst. So there we have one class, route handler, seems to have a very low grade. So if we should sort of try to get a better grade on this software, yeah, we should choose that class and inspect that more thoroughly. We can also see the rating the PHP operation. So each operation or each method, here each method of the class get a grade. So here we can see that the handler's controller action on top there, that has a D, and maybe that is the worst rated part in this sort of as a method. So here we can see what are the methods we should go into a bit deeper if we want to improve the quality of this particular code. Okay, so there we go. So now we have badges for building a project. That's saying that the whole build process, like make, install, make, test, that worked. And we have a visualization of code quality that goes now beyond the grade of 1 to 10. So we have more metrics on each part of the project, the classes, the methods. So how could we go about then visualize the code coverage as a quality measure and how we can use it? So, or can we? So this is a code coverage badge. It's also taken from the Scrutinizer quality tool. So this is saying it's saying how many lines of code are covered by the unit tests. So it's pure code coverage. It doesn't say that there are good tests. It doesn't say anything about how many tests there are. It's just saying this code is covered by unit test 90% lines of the code. Okay, but I can still relate. I don't have to imply that this is actually good test, but there are tests here. These tools that are giving us a better view of what is tested. Here is a good view I find, because sometimes there are several parts of an application. It's just not only the source code that one could do unit test on. We could also see here that there is a configuration directory with code in it that is also covered by unit test, and that is a good thing. So yes, not only the source code. That's a small quality thing one can see when we go into deeper here. And we also see that the code coverage is 96% of the source. Config has 100%. We can also see then visualizing that how much is the different classes. So this is a code. This is a source module. The module has several classes in it. And here we see that sort of the route handler has 91% of code coverage. And we also see that it's relating to the size of it. And that is good. You're starting to use one metric and relate it to another one. So there we can actually see, on taking the route handler up there, it's 91% of 41 lines. 411 lines. So it's approximate like 40 lines of code that I need to cover more. So how much time would it take to write unit tests for 40 lines of code? Well, it depends, but still we can sort of get it more understandable when we put this into context to each other and comparing metrics with each other. On the other part here, we see the methods and how well they are. We see how many lines there are, and here we see some kind of crep score. We don't know what crep score is yet, but we can see that the low crep score there, on 5 and 6, they are green, and a higher crep score like 21 or 50, and at least 21 there has a yellow value, so that is not good. So giving this sort of a rating here, we can see that the crep score might be bad, and the number of lines we are talking about in this method, 65 lines. Okay, I can relate that to, there is a lot of lines, 65 lines or a lot of lines, and a high crep score. We must see what the crep score is. Let's get back to that. Okay, so can it be useful to show off a code coverage badge like this? I say yes, it would. It shows off to interested parties that to what context do I have sort of working with code coverage in my system here. And if I put up these code coverage 97 green, 56 yellow, 16% red. So which project would you like to work in? Would you have the green, the yellow, or the red badge? Yeah, okay. So I think I'm gonna go with the yellow or the green. I do see that the red one there, it has a lot of unit tests needing to be done. So I do think they should do some work if they want to have better coverage. Still, this doesn't say anything about how good this software is or how useful it is. It is just telling us about the code coverage, and that is what we sort of can relate it to. A bit more about this sort of grading of the software. So how is it done behind the scene? So here we can see how they are sort of grading or rating the classes. So here we have 4 classes. On top there we have F, which is the worst grade. A is the best grade then. So, but what are the other columns here in this table? So we see something about coupling. Okay, we have a coupling there. We see something about cohesion. So cohesion. We see size. Size should be how large is the programming. perhaps number of lines of code or something like that. We have a complexity value. Okay, here we can, yes, we can relate here that the complexity of the top class there seems to be very high compared to the other ones. Maybe that is one reason why they sort of rate it so badly. Maybe it's a complexity issue. Okay, and now we have the test coverage. How much of this class is actually covered of unit tests? So it seems like this rating perhaps is sort of, the final rating like F is sort of saying that this is troublesome, and it may refer to coupling, cohesion, size, complexity, and test coverage. Okay, then we get some more perhaps hands-on to work with, but we still need to understand what they are, this coupling, cohesion, and complexity. Here is another one, and it's still from the Scrutinizer project. I think it's a nice project helping me to understand code quality a bit more. So up here we have grades by method. So here we are still being graded from A to F. So the worst one there is D. And then we can see what columns we are. We have duplication. This is code duplication. How much code is duplicated here? Okay, and then we have a size measure. So how large is it? Perhaps lines of code. Then we have the complexity measure again. So how complex is this code? And we can see there complexity, as higher the complexity, the lower the grade. Okay, so keep down the complexity to get a good grade. Okay, they are gonna remember that. Here we also have the crap value. We don't know what crap is yet, but it seems to be low crap value that is good and a higher crap value that is bad. Do you think that these are indicators of code quality? Yeah, I think we need to learn a bit more about them before we proceed then. So, software metrics. Can they really be indicators of software quality? And what kind of metrics are actually used when someone is saying that your software is graded as B? How can they do that? And what sort of values or decisions are they sort of basing this judgment of? And all these metrics, can they somehow help us a bit more to relate to what is good and clean code? And can they help us sort of somehow, to some extent, indicate what is good code? Well, let's see. So, taken from this Scrutinizer project, we saw that when they did metrics by the method, they looked on duplication of code, size code, the complexity of the code, and something that was they labeled the crap score, and a bit about the test coverage. And when they did the same thing, metrics by the class, they had values for coupling, cohesion, code size, complexity, and test coverage. So let's put these together. So these are metrics that seems to be very used and sort of giving us different grades of our code. So let's look a bit more on these into detail, and let's try to understand how these metrics can affect the sort of perceived code quality that we can show off from our code then. Size. Let's start there. Should be an easy one, I imagine. That is just calculating the amount of lines of code we have in our code base. So, of course, we need to separate the lines of code in sort of, well, at least count, remove the empty lines, calculate the number of comment lines separately. So I think I have an example here. So this particular small code here, that should have sort of 4 physical lines of code. So that would be the lock or source counts of source lines of code could be also lock or slock. So it's 4, and they are including the curly braces here. The LL lock would say 2 logical lines of code, the for statement and the print statement. And it will calculate 1 comment line. So 1 comment line above there. So these calculating the size of a software like this could give us a feeling on how large it is. We should also be aware that the way people calculate the size of software may differ a bit between programming languages and also a bit between the tools. So we can see sort of different definitions of what's being sort of logical lines of code or source lines of code or lock and so. Let's just review one of the projects here and see if we can sort of understand anything here. So this is saying that we have logical lines of code like 267. Okay, so we know how much 267 logical lines of code are. We can relate to that. We can see that there are some classes here. The average class length is 33 lines of code. Okay, 33 lines of code like this. But the minimum class length is 0. That is usually when you sort of create a new type of exception or so. The maximum class length is 93, so it's almost 100 lines of logical lines of code, removing the curly braces and removing the empty lines and removing the comments. So it's fairly sizable class, perhaps one could say. And we see here a bit more average method length, 5 lines of code. So we have rather small methods in here, only 5 lines of code in a sort of as an average. And the maximum method length is 26 lines of code. Yeah, maybe that's a bit big, but it's not yay big, but we should sort of try to get, I would say that try to go with methods that are not more than 10 lines of code. And if you have more than 10 lines of code, consider if you can refactor your code and write it out in more methods. So each method is being smaller. And then with the average methods per class, okay, it's 6. And we see maximum methods per class, 23. So we have one class here that has had 23 methods in it. Okay, seems to be a rather large class. Sometimes you hear a guidance saying that, okay, try to have not more than 10 or 12 methods per class, something like that. But these sort of these are only guidelines, and it all sort of depends on what type of class you have. Okay, so let's just see a bit more. This is just size by structure. We can use the size of the code and divide it into, categorize it. So here's categorized into how many namespaces do we have, how many classes do we have, what type of classes are there. There are concrete classes, non-final. So this look and view when you do this dividing of size into structure will look a bit different depending on your programming language you have. Non-static methods 49, public methods, private methods. Okay, so we get a feeling on how the code is organized by reviewing it like this, using size by structure. So here we say global, we're having constants or class constants here, 2 class constants. Yeah, that's fair. If there was someone saying here we have global constant 0 here, if we had like 20 global constants, that would be perhaps something saying, okay, let's look why do we have so many global constants here? So it can be, this type of size can be used to relate to how sort of perhaps how complex the software is, how large it is, how it is divided, and what type of code structures it's generally using. So still, it's a long report, can be hard to sort of relate to at first step, but it is useful as a starting point for doing metrics. Code duplication is another metric then, and that is it indicates the amount of source code that is duplicated, what you have done copy and paste on, and it provides you with a sort of a guidance. These are the sections of the code that you could perhaps rewrite into methods, into classes that is a bit more reusable. Code duplication is not desirable because it's in general associated with sort of higher maintenance cost, and it also could be sort of indicating that not too good design in this software module. Why do you have this large amount of code duplication? So be aware about, try to avoid code duplication, at least when we're talking about having a high quality measure of the code. Code duplication is usually sort of measured in the percentage of the number of lines that is part of the duplication. The tools that are analyzing this, they are often showing up what code sections that are code duplicated, and then one can go in and review these code sections in isolation and see, can I do something here? Can I sort of write it as a method? Why does it look like this? Basically, code duplication is not too good, so try to avoid it. Cohesion is a really good thing to learn a bit more about, because if you have sort of high cohesion in your module or in your class, that is generally saying that this is a good thing, and this is actually sort of an indicator of good and quality code. So cohesion is measured by LCOM, or lack of cohesive methods. And it is a degree to which the elements inside the module belong together. So they need to belong together. It is also a measurement on how many features are your class performing. So how many things are your sort of class performing? And having a class that performs one thing, one feature, that is good, because it's crystal clear what this class is going to do. But when you have a class that performs many features, that is generally sort of, well, do these features actually belong together, or should they be sort of separated into their own modules? So this is what cohesion is trying to tell us. And here is a calculation of LCOM. Here is an LCOM of 3. So it basically built using a dependency graph. So here we have at the first line, at the 1 there, so it's a use case where we use the class. So go to, we're driving a car and we're stopping the car. So all of those are sort of related to each other. And then we have another feature of the class saying, oh, I'm getting angry and it's using my brain. But that is not related to the first use case. And then we have a third use case, just say drink coffee, and it's not related to the other ones. So here we have an outcome of 3. So this class has 3 different responsibilities, and it would be ideal if this only was 1, because it would be a sort of more cohesive module being 1. 3 more features supported and not so high cohesion. Okay, let's remember cohesion for now and go into coupling. These are sort of a bit related. So coupling is a sort of a degree of how a software module is dependent on other modules. It could also be a measure on how many modules are depending on this module. So if this is my module, how many external dependencies do I have? And how many are dependent on me? So this is calculating how, taking 2, 3, 4 modules, how tight coupled are they? Are they sort of loose coupled or tight coupled? Loose coupled, they are sort of, they have not too high coupling to other modules. We call these loose coupled. And if we have a sort of high coupling, then we are having a module that are very much depending on other modules. They are tightly coupled, and that could be a indicator of bad, costly software, because when you change in one of these modules, you need to sort of check all the related modules that they actually work. So it could sort of higher cost of maintenance because of this tight coupling to other modules. The metrics behind coupling is then can be measured in 2 ways, where we have efferent coupling and afferent coupling. So the efferent one is for the outgoing dependencies. So how many other classes do my class depend on? How many outgoing dependencies do I have? The efferent coupling there is how many incoming how many are dependent on me. And general way of calculating this coupling is the instability index, and that is only taking into account the outgoing coupling. So how many modules am I dependent on? And when we have sort of a high number of outgoing coupling dependencies, then it's trying to reach almost up to the value of 1. That means this is highly unstable, since it's very tightly coupled to other modules. And when we have a value of 0, it means a bit more stable, since it's loosely coupled, or it has non-couplings to other dependencies to other modules. Okay, good. So what we should have sort of low coupling, high cohesion, or loose coupling and high cohesion. So low coupling or loose coupling, that is often a sort of sign of well-structured design. And when we combine this with high cohesion, so we're getting a sort of software metrics that in general shows us that, yeah, this could be the 2 things that is actually pointing out your software to be good, clean code, easy to read, easy to maintain. So remember that. Low coupling, high cohesion. That is what we are striving for. Few dependencies to other subsystems, and the things I do in my class, I do that well, and I don't do a lot of other stuff. I only do one feature, perhaps. Low coupling, high cohesion. This is good to bring with you when you're actually writing your code. So try to remember those, C and C, cohesion and coupling. And do also try to get this one, the complexity. So it's a 3 C's here, cohesion, coupling, and complexity. Cyclomatic complexity is a software metric, and it's used to indicate how complex is a program. Okay, so it's a measurement, and it's generally saying how many decision points are there in this code. And if we're taking one method that's just returning another value, that would have a cyclomatic complexity of 1. So that's where we start. And if we have a method that has several decision points, Well, for each decision point, we are sort of incrementing the complexity. So if we have a value of 10, that is a method that would have sort of 10 decision points in it, or actually 9 decision points plus 1. That's 10. When we calculate this cyclomatic complexity, we actually viewing our code as a graph. So this is a directed graph that sort of representing the code we have written. And it's starting there in the red dot. So we go from the red dot, and that's a cyclomatic complexity of 1. Then we comes to another white dot, not a problem. Then we comes to the second white dot. And there we have sort of a decision point. We can go left or right. So cyclomatic complexity gets 1 more. And then we continue to the next white space there, and there's a new decision point. So we go left or right. So now we have a cyclomatic complexity by 3, and then we continue to the end. So this graph here is showing a cyclomatic complexity of 3 with 2 decision points then. So to make it easy and just put a code sample in front of you, we have this code sample here. It's just a method. It's not doing anything else. Everything is not tabbed in. It's returning true. So this is the cyclomatic complexity of 1. That is the best we can have. No decision points. But how is this? Here we have sort of 7-ish decision points. So if we start on the top there, we have a function. So there we start, 1, complexity 1. Then we have an if statement. There's a decision point, so we go to 2. Then we have another decision point, we go to 3. Then we have an else if. Then we go to 4. So 4 decision points, well, 3 decision point plus the start value 1. So then we have an else if. And while is also a decision point here with an expression in it, and else. So more or less this function we have in front of us is then having the cyclomatic complexity of 1 plus each decision point being a cyclomatic complexity of 7. Then you can imagine how would a function looking have a complexity of 10? Well, it would have even more decision points than this function here. So yeah, a 10 well, it is complex, a bit more complex at least. So these decision points, we try to avoid them. And maybe you've heard before that we shouldn't tab in our code. So when we have code that is not tabbed in, so it's just straight line, read up, down, not tabbed in, that is in general easier to understand and read code. And here you can see sort of each tab here becomes 1 more complexity value in this cyclomatic complexity calculation. So each tab makes your code more complex. That could be a good thing to remember. So try to keep your code narrow, straight. Don't try to don't make too many tabs, because it in general makes your code a bit more complex. Here is just an overview where we sort of relate the complexity to the code size. So yes, now when we know what code complexity is, we can relate it to the code size. Let's see if we can find everything. So average complexity by class. So it's a 19. So each class in general I have almost 19 here of complexity. Okay, maybe I can relate to that. The maximum class complexity there being 77, and the minimum is only 1. So 1 is a not complex class, but 77 decision points in that class. Yay, something's happening in that class. Okay. Here we see an average complexity by method being a CC4. Okay, 4 decision points, not too many there. And we see that the maximum method complexity here seems to be 19. So that is 19 decision points in 1 method. Well, maybe one wants to look at that method a bit more and see why is it that complex. So if we want to provide a guideline for this cyclomatic complexity, it would be that cyclomatic complexity for modules should not exceed the value of 10. And if it does, consider to split it down into smaller modules so that this cyclomatic complexity of the module does not exceed 10. And depending on if we see here, if we relate the module to a class or we relate it to a method, I do relate this to a method. So try to avoid methods having a complexity of less than 10. Try to do that. Try to have your methods with a cyclomatic complexity less than 10, just as a guideline. And of course, like we say here, if there is some reason that this module must be more complex, well, fine. Maybe you can say a note about it and saying you have reviewed the code and yes, you know it's complex, but for now it's okay, and then you can leave it. That could also be a good way sort of to dealing with it. So it's not per se bad in having a complex code. It's just that in general it's better to have less complex code than it is to have complex code, at least when we are calculating software metrics. So yes. The CREP score, we heard a bit about that, and before from the scrutinizer here. And so the CREP here being something change, risk, analyzer, and predictor. So it's trying to give us a score on how risky is this part of the software to go into and change, or sort of how much amount of work do you need to make this crappy method a non-crappy method. So it's trying to show us you have a troublesome method there. It doesn't seem to be good from the CREP score point of view. And the CREP score is sort of saying it will take you this amount of time to get back on the no CREP territory. And broadly speaking, sort of a CREP load of n sort of indicates that you need to write n tests to bring the product below this acceptable CREP threshold. So the CREP score is sort of relating complexity with how well tested the software is, how much code coverage we have. Here is a view of this where we compare the method's cyclomatic complexity. So you see here, if we have a very low cyclomatic complexity, like 0 to 5, then they say, okay, we don't even need sort of any coverage of that code to consider it as a non-crappy one. But if we have a complexity of 10, well, maybe you should go up to 42% of code coverage to have that complexity balanced with the units test. And if you go down here like 25 in a cyclomatic complexity, then you should sort of indicate here saying you need to have a code coverage of 80% to be on the right side of this crappy threshold. So CREP score is trying to relate the values of your code's complexity with how well tested it is. And it indicates how much more tests do you need to write to make that a non-crappy method. Good. There are more software quality metrics out there, and I'm just going to mention a few of them. I'm not going to go into details, but I just want to let you know about them. So here we have the Halstead complexity measures. It's actually a family of metrics sort of giving us program vocabulary, length of the program, calculated program length, volume, some kind of way to measure how large the software is. We have the difficulty, so how hard is the program? Maybe that is a sort of some complexity within it. How much effort would it take to write this code or build it code from scratch? And time to require to program it, and even trying to measure how many delivered bugs will this program have. So this is all about trying to use quality metrics a bit to partly estimate the work effort you need to have before going into this project. So that could be a good thing, trying to relate the size of code and its complexity to how long it will take to sort of build it. It's a hard figure to sort of put into context, but still, that's what it's trying to relate to. Maintainability index is trying to say how well a part of the code, how maintainable it is, how easy is it to support and change. And the formula behind it is using the Halstead volume then. It's using the complexity, cyclomatic complexity of the code, counting the source lines of code and the percent of comment lines. Here they are actually sort of relating the percent of comment lines to how easy a software is to maintain. Good or bad? Well, that is how they do it. So then we're also trying to visualize this between 0 to 100, where sort of green is in the range of 20 to 100, and that in general means, well, it's fairly easy to maintain this. So this is a metrics that we could find in Visual Studio Editor, and Microsoft is using it to sort of visualize in the editor the tricky parts of code. So that's a good, all this visualization I think is a good thing, because it makes it easier for us to relate to these metrics and also make use of them in our day-to-day coding. Okay, so this is a lot of metrics we have here. So how are we going to produce them, and how are we going to work with them? What are the tools we're going to need to sort of make better code, perhaps? So let's see here. I have a sort of few suggestions, and these are programming language agnostic. These are ways I propose you work with the code independing on the programming language you are in here. So I'm using Make here as a build tool, and if you have another sort of programming language, you might have another build tool. So this is just sort of saying, okay, let's have a make test to test the software. Have a make lint, make the linters run. Let's have a make metrics that calculate all the metrics and maybe visualize them in a report to make it easy for me to understand them. So let's see more about these just tools behind the scene that I should adapt, because these tools are aiding my work effort into producing high quality code. So code standard is one thing we should always bring with us. So I'm just proposing make CS if you just want to check the code standard. So follow a code standard, and you should use tools to verify that it is followed. And then there are a lot of different tools depending on what type of code standard I have or what type of programming language I am. But always use it. You should also use these linters and mess detectors. So they are flagging programming errors, bugs, suspicious constructs. They're doing the static analyzing of your code. So it's general, not executing the code, just analyzing. And we have a lot of different tools that can do this. And sometimes they include a copy and paste detector, or you need to run an extra tool to use to get the report from the copy and paste detectors. And these mess detectors, they're not saying that our code is bad. Well, yeah, they are, but our code might still work. It's not an issue in it. They are just saying us that as a general rule of speaking, you should try to reorganize your code here because you're not doing it in the best practice way. So they're trying to help us avoid like possible bugs, dead code that could never sort of be reached, unused variables shouldn't be there, overcomplicated expressions, do we really need this else statement, perhaps duplicated code. So these sort of mess detectors are providing us with an insight into our code where we could do better constructs according to those guidelines. Code metrics. Yeah, that is, well, about the stuff we talked about today. Calculating the size. We hear, like I said, the 3 C's: cyclomatic complexity, coupling, cohesion. These are 3 C's that can actually help us writing better code. So loose coupled code or low coupling, very high cohesion, software modules doing only one feature, keeping it together, and keeping the code straight, not tab in to increase the cyclomatic complexity. 3 C's that might actually help you write better code. So make metrics is just running the code, gathering the metrics report, and we also would like to get this a bit more visualized, but at least this should be a part of every development environment, if you ask me, because when we start to calculate it, then we can do something with it. So it's the first way to go there. Make test. Just run all the test and coverage. Perhaps you also run the linters, maybe. But this is also generating this metrics on the tests and on the code coverage. So I'm basically trying to give you a few routines that your development environment should support. It doesn't mean to be this make command. You can have it in another way. But these are the tools and techniques and utilities and processes that you should work on a more or less daily basis when you're developing your code. And this will, for sure, help you to sort of reach a better result on all these badges. And you should use these badges because using and visualizing these tools, visualizing will give you will give the other people looking at your software some kind of a good feeling, small ponderance of evidence that shows that, yay, this might be a quality software. At least it has some properties of that I relate to as a high quality software. I cannot say that it is high quality, but it has some kind of properties that relate to it. So maybe it looks good to be of better quality. Yeah. So use these parts. When you include these tools in your development environment, you are all ready to go with these automated tests. And you can connect systems like Travis and Scrutinizer, then can create this type of quality reports, doing automatic builds, and then you can get those badges to show off. So this is a good place to start to work a bit more within the sort of code quality area. And a small note about these validators and linters, mess detectors. They might give you some statements or guidelines that you don't agree on, or you find them very disturbing and not correct. But you should always, and I say in general, always, try to listen to what the linter and mess detectors are trying to say to you about the code. And you should, if you somehow choose, I don't agree, then still, you should go behind the scene, read on what the explanation is about this message, why the linter is saying that you should do it in this way instead. And then you should try to figure out, why is this good, and why does this seem to be a property of good quality code? Because there are so many things to learn here on small parts on how you can create good code. And don't sort of avoid the opportunity of using the linters and mess detectors to do this. So don't blame the messenger, use it to improve your coding skill. So let's try and sum this up. So for now we have talked a bit about badges, metrics and indicators of good quality, and also go into the sort of deep behind if your code is rated 6.4. What is it actually based on? And I think a few things you should sort of bring with you from this. Well, you should try to adapt these badges and quality systems and use them to show off how your code is looking. And when it comes to day-to-day coding, I think you should sort of remember these 3 C's. So code complexity, coherence, and coupling. Coherence, coupling, complexity. Try to sort of remember what those 3 stood for in your code, and when you try to write code that is adhering to the values of those, you will in general get a result of better code, at least according to all the quality metrics, and your code quality badge will be more green if you do so. So here is a view in general of how one could use the badges. And we see here that this is for the code coverage part. There's a lot of modules here in this software. So we have a code coverage part where we're having 2 modules being red, 2 modules being yellow. So perhaps if we want to improve the overall code coverage of this project, those are the 4 modules we should go on and work with, because the other modules are all above 70%, and that seems fair. Okay, so that is what those badges might be telling us. Looking at the code quality column there, we see that the code column here is the code quality in general perceived as high. There are 2 methods or 2 modules here having a yellow code quality, and perhaps those 2 could be modules that one would put some bit extra effort into, at least maybe not rewrite, but at least look harder into if this is an acceptable level of code quality in these 2 specific modules. Maybe it is, maybe it's not. We can also see, if we combine these 2, that the code quality and the code coverage, they're both yellow on this text filtering buffer at the bottom. Perhaps that is an indicator that this particular module could be an area of improvement for the next release of our project here. These are examples from the three projects I used here when I'm talked about the badges. So this is from the Scrutinizer website, and this is how it looks like when I'm looking at the report I get. So each time I check in this code into GitLab or GitHub, the Scrutinizer will check it out and sort of create this code quality report for me. So here is a 10, very good. I see the code coverage is not too bad. Well, it's 56. Maybe I should do a bit more there, and then it would also be green if I just sort of increased it. You can also see here on the log there saying that last time I did something here, I increased the code coverage by 70%. So we see here I get a history of working with the code coverage. So yay. But still, 10 as a quality seems to be a good module. If I take this module on the other hand, so the log there saying I'm sort of introducing new bugs, or I'm making one method worse than before. So here, this was the 6.4 grade. It is, on the other hand, it has a very high coverage. So it has 97% of code coverage. So maybe I'm trying to write more tests on this module since it has a bit more. Maybe it's a complex. It's a router saying so. A router might be a bit more complex software module. So maybe this is a bit fair. We don't know that until we go behind the scene, but we need to put this, we get these metrics and we need to put them into context. What is this module actually doing? And maybe 6.4 is fine for this. At least I know I have a measurement of it. Here's another one. This was the example of the 4 quality product, where half of the code in it is actually red, and we see rated critical. Oh, it doesn't feel so good. And introducing new critical errors. And we see a code cover of 16%. And we see the status build is failed. So it's a lot of red issues here. But you know what? These three software programs I showed you, this is one of the most, this is used mostly of these, and this is used on an international level. And it works basically flawlessly without getting any bug reports and so. So this is an example of a software that has high quality when it comes to executing in the customer's environment. It works, it does not fail, it's useful. But still, when we get up the quality metrics for the software, it looks bad and not even the build is working. So it seems like the environment around this project is not up to sort of the grade one would like to have it. So maybe that is a signal that this project is a bit troublesome to maintain and further develop. And that is, yay, actually true when I consider it. Good. So all about this, is this actually used outside in the industry? Yay. And it's like always, it depends. Some use it, some don't. I do think that this is for sure an indicator of the maturity level of the development organization within that. Each of these tools that we are talking about, each of these metrics, tools that they're using, takes time to implement and adjust and understand. And yes, it is fine if we just start working with a few of these tools. But when we have done that, we should also try to invest time in learning the tools and learning what they are saying us and learning how to sort of work with the outcome of the tools to improve our software. We should go that step also, not only collecting the data, but also trying to push the data to be better. It is quite popular nowadays to work with these software quality tools, and a lot of this is because we're using Git for versioning our software, and we're using GitHub or GitLab to publish it. And when we publish it to those services sort of can sort of initiate, build a workflow or build pipelines, sending the software to external services, doing sort of checking out my program, building it, installing stuff, running tests, running the linters, and checking that it is sort of healthy. So it's quite easy now to sort of add on software quality services when you have started a flow of working with Git, GitHub, GitLab. And I do think that each programmer should choose to use these tools on their own. And then if you go to sort of a company that is not using them, still, I think you should try to use them, because it will make you a better programmer, at least in the context that you're trying to learn from all these linters and quality metrics, and you're sort of thinking of your code. How can I write my code in a better manner? And then you have all these tools that actually can help you do that. So what about research matters? I did what I usually do. I just looked through some of the recent research papers based on code quality, where they use metrics to sort of create this. So we got here some about code quality issues in student programs. Okay, can relate to that. Got code quality of open source software development, using metrics to predict code quality online. Okay, so large scale study of programming languages and their code quality, using GitHub as a sort of study object. And the last one here is trying to sort of just external code quality. How does that correlate with programming experience, or is it just a feel-good factor? So being everything in general that is easy to measure and might have a added value if it gets good sort of measurement of being able to analyze it is sort of researchable. And having all these metrics that I've talked about today, of course, when you take a program and you put all these metrics into context and you try to relate them to sort of other values, you have a good basis to form a research project of this. So yes, for sure, software quality metrics, that is a very highly sort of researchable area, and it's fairly easy to sort of gather a lot of data and then going in to analyze it. And this was all I had today. This was an introduction overview of the code quality metrics, and a few of them there I told you. Remember the 3 C's? You can use them on a daily basis to actually try to become a sort of a better programmer, writing better code. And you should also try to get these badges. So when you're working on a project, try to integrate your project into these type of build tools, code quality tools, and that could actually be a way for you to continue on your path in how should I write better and cleaner code. And using all these metrics and validation tools around it will give you a sort of good basis to work from. So that's all for me to now. So very nice to see you, and I see you soon again. Have a nice one. Bye bye.